Everyone. My name is Yongsu from the Engineering Practice Division at Seoul National University. Today I will present an analysis of energy savings through moisture control in compressed air dryers used in display manufacturing processes. This presentation will proceed as follows. As you can see, the presentation will cover the research background limitations of the existing system, research objectives, experimental design and methodology, experimental results establishment of moisture control standards, and energy savings analysis research summary, and key findings, industrial impact, and contributions to sustainability research limitations and future research directions. First, I will explain the research background. Compressed air is an essential utility in the electronics industry. In display manufacturing processes, compressed air is used for cleaning, drying, cooling, coating, transport, and inspection. However, excessive moisture in compressed air can lead to process quality degradation and equipment corrosion. To prevent this, adsorption dryers are used. Now let's discuss the operating method of the air dryer. Adsorption dryers operate using a two-tower system, where one tower supplies air while the other regenerates. However, the current time-based control method switches towers at fixed intervals regardless of actual operating conditions, leading to unnecessary energy consumption. Therefore, a system that monitors moisture levels in real time to determine optimal operating conditions is needed. Next, I will explain the limitations of time-controlled adsorption dryers. They cannot adequately respond to changes in inlet air temperature. They do not operate flexibly according to production or load variations. The following graph illustrates the trend of temperature and humidity variations over 2 years in Korea across different seasons, along with the corresponding trends in inlet temperature and humidity of the dryer. The second trend represents the operating load of the dryer over 2 years. As you can see, the conditions continuously fluctuate, and although the average operation remains at 70%, the time control method fails to adapt accordingly. Now, let's introduce previous research. Due to energy concerns and inefficiency, various dryer operation methods, such as dew point control and flow control, have been studied as shown in the table below. However, the dew point control method responds too quickly to dew point changes, posing risks to supply quality, while the flow control method does not adequately respond to humidity variations. Therefore, this study proposes a moisture control method to address these issues. Now let's move on to the research purpose. The objectives of this study are to develop a real-time adsorption moisture monitoring system, verify adsorbent performance through experiments, and determine optimal operating conditions, and apply a moisture control operation method to quantitatively evaluate energy-saving effects. Now let's discuss the configuration of the pilot installation. To validate this, a small pilot system was installed reflecting design criteria applied in the electronics industry. The pilot system was operated under real-life conditions, and 5 experiments were conducted to measure actual adsorption capacity at the point of dew point change. Key components include the S430 sensor for real-time airflow measurement, the S211 sensor for inlet air dew point temperature measurement, and the S220 sensor for outlet air dew point temperature measurement. Using data from these new sensors, we calculated the moisture content of the inlet and outlet of the compressed air, then applied an algorithm to obtain real-time adsorption moisture data. Through this, the performance of the adsorbent was evaluated. Based on the experimental results, moisture control operation criteria were established with theoretical energy savings estimated at approximately 32.3%. Now let's review the experimental results. This study monitored real-time adsorption moisture using a pilot system and verified the effect of moisture control compared to the existing time control method. The results confirmed the deterioration of adsorbent performance at the dew point change point and provided actual performance data of the adsorption tower. A total of 5 experiments were conducted with results presented in 5 graphs. Each graph shows dP changes over operating time adsorption data and flow data. Based on this, the maximum accumulated moisture adsorption was measured for each experiment. The average accumulated moisture amount was 5035.6 G, with a minimum of 4296 G and a maximum of 5930. 5913G. Based on these results, the optimal switching point of the adsorption tower was determined. Operating under the minimum moisture criterion of 4296G ensures a conservative approach, while applying the average criterion of 5035.6G maximizes energy savings. Compared to the energy consumption of the conventional time control method at 70% load operation, the minimum moisture criterion achieves 88% energy savings, while the average moisture criterion achieves 91% energy savings. At 100% load operation, the minimum moisture criterion achieves 62% energy savings, while the average moisture criterion achieves 67% energy savings. Additionally, it is necessary to introduce a safe operation standard considering dew point temperature changes to establish a more reliable moisture control system. Now, let's conclude the study. This study analyzed energy savings through moisture control in compressed air dryers used in display manufacturing. It was confirmed that the conventional time control method does not fully reflect operating conditions, leading to unnecessary energy consumption. To address this, a moisture control method based on real-time moisture monitoring was applied, demonstrating energy saving potential. The study's key conclusions are that the time control method does not account for load variations and operational changes leading to excessive energy consumption. The moisture control method utilizes real-time data to establish optimal operating conditions, maximizing adsorbent performance and enhancing energy savings. Applying the verified operational method could achieve annual savings of 1.4 GWH in electricity and reduce CO2 emissions by 630 tons. Future research will expand in several directions. Additional studies are needed for large-scale applications beyond pilot experiments. Long-term validation in real industrial environments will be conducted. Monitoring adsorbent performance over time will help establish optimal regeneration and maintenance strategies. Comparative studies of different adsorbent materials will be conducted. A comprehensive economic analysis is needed to assess the feasibility of the moisture control method. Factors such as initial investment maintenance costs and energy savings will be considered to develop an optimal operation model. The expected cost savings in large-scale production environments will be evaluated. The proposed moisture control method can be linked to smart process control systems for more precise operation. Research will be conducted to develop automated compressed air dryer control technologies using data-driven automation. Thank you for your time. I hope this research provides valuable insights into optimizing energy efficiency in display manufacturing. I appreciate your attention and welcome any questions you may have.